the Line.
Hey guys, turns out technology is really hard. Good evening, everyone, and welcome to Season 3 of Behind the Lines, where we bring the experts to you. I'm Ty Tremblay from GameSense, along with Evan Morrison, and this week we'll be discussing drivetrains. Tonight we have a presentation on the topic, followed by 30 minutes of Q&A with you, the audience.
It's our opinion that every technical mentor and student should be well-versed in drivetrains, and we're fortunate to have 4 fantastic experts tonight, including myself and Ty as the hosts. We do need to mention that the views expressed on Behind the Lines by hosts and guests are those of the individual and do not necessarily reflect the views of first participants.
Don't forget that through the entire show, you can submit questions to us by tweeting at FRC GameSense with the hashtag FRCBTL. You can email us at btl@frcgamesense.com, or you can type your question in the Twitch chat with !Q followed by your question.
With that, we're excited to have 2 other experts with us today. Clint, please tell us a little bit about yourself.
As you said, my name is Clinton Bollinger. I'm with Team 2337. I'm going on my 13th season of First. It'll be our 10th season for Team 2337, the Engine Nerds. My role on the team usually has to do with robot design, the build, and I'm the field coach during competition.
Awesome. And then our other guest tonight is Nick Lawrence.
Hi, my name is Nick Lawrence. I'm currently a mentor for FRC Team 3940 Cybertooth. I'm also a mechanical systems designer at AndyMark. I'll be going into my 12th season of First this year as well.
Awesome. A lot of long-time firsters here with a lot of knowledge to share. So let's get right into it. Okay, so tonight we're talking about a problem-solving approach to drivetrain design. And what we mean by a problem-solving approach is being able to identify the specific tasks and the specific items within a game, a first game, obviously, that you're trying to solve with your drivetrain, as opposed to saying, you know, I see this game and I think that mobility is important, so I'm going to build a swerve, right? There's a little bit more to it than that. Next slide, please. So there's 3 platforms that we're going to be talking about with drivetrain design. We're going to start with the fundamentals at the bottom, and that's mainly around consistency. If your drivetrain isn't consistent, then it's hard to do anything else well in the game. On top of that, then there's advanced topics, and so that's more talking about optimization, being able to play the game better than just your average team. At the very top, then there's expert level. This is for teams who have a lot of experience, who have a lot of history of being able to do the first 2 well, the consistency and the optimization, and are looking to be able to actually get an advantage over their opponents through particular use of their drivetrain. So with that, we're going to start with fundamentals. And we call this fundamentals because it really is the absolute basis. You should not be building any drivetrain that doesn't do the fundamentals, regardless of your levels of experience. I'm actually going to point to the quote at the bottom. You'll see this come up a lot. A lot of people have said this. I like to attribute it to Ken Zabalos, one of the former mechanical leads on Skunkworks Robotics. And he talks about how drivetrain cannot win you the match, but it can lose you one. And that's really the core of this. What an FRC drivetrain is supposed to do is get the robot where you want it to go, when you want it to get there consistently. And that speaks to robustness, ground clearance, proper speed selection. Everything else on top of that is gravy. If your robot isn't getting to where it needs to go, you're not getting a successful, you're not being successful in the match.
It doesn't matter how good your intake is. If you can't ever get to that game piece, doesn't matter. It doesn't matter how good of a scorer you are. If you can't get from point A to point B, doesn't matter.
Exactly. Next slide, please. So getting where you need to go. This is the first point. If your drivetrain fails, the robot doesn't get where it needs to go. Failures can be mechanical failures, such as a chain breaking or a gearbox shearing out, or a motor burning up, or a design deficiency, such as not giving yourself enough ground clearance so it gets stuck on an obstacle. If either of those things happen, your drivetrain hasn't succeeded at the first point, which is it's not getting where it's supposed to. You want to use the game analysis to figure out where on the field you actually want to go. Sometimes it puts certain constraints on your drivetrain, such as if you need to be a certain size, such as for the 2010 game Breakaway, if you wanted to fit through the tunnel, that was going to restrict your drivetrain size. Similarly, in 2012, when we had the bridges, if you wanted to be able to do a triple balance, that was going to likely restrict your drivetrain size. And we saw a lot of teams do maybe non-conventional shapes in both of those years in order to get around those. Or if you need to go over or under any obstacles, such as this past season in 2016, whether it was the low bar or going over the rock wall or going through the moat, which got a lot of teams hung up, understanding the kind of clearance that's required so that your robot doesn't get stuck, isn't out for the match, and potentially costing your team and your alliance a win.
Even another... Go ahead.
I think the 2016 game really drove home how important, or really refocused how important the drivetrain is, in that it made it so you could score a lot of points with the drivetrain, that's for sure. But also, if your drivetrain was poorly designed or broke easily, then you were almost useless on the field.
Yeah, the thing I was going to say was 2015. I think that year there was subtle things about the scoring zones that you had to go over, where the kit apart chassis had a 4-inch wheel, and just having that slight and additional 6-inch wheel made a huge difference of how well you went over that. And some people kind of ignored that and didn't look at it. Like I said, so there's sometimes these subtle things. Even in 2010, there was a little bump transition to get to the big bumps that a lot of people miss those subtle details.
And there were 2 layers of carpet in 2013 as well, that some people, they saw the field was flat, so they built with maybe a 1/4 inch of ground clearance, and you saw some robots getting stuck under the pyramid as well.
Absolutely. Yeah, next slide, please. I think we actually talk about this right here.
Yeah.
Ground clearance. We recommend at least 1/2 inch. Most drivetrains are going to have about 3/4 to an inch of ground clearance. That 1/2 inch is really, really important for the reasons we just mentioned. Very frequently, extremely frequently, first put some kind of plate or plywood or some kind of lip on the field underneath the carpet, leading up to a structural element to make sure it has a big enough base to stand up. That creates a lip in the carpet. If your ground clearance is less than that lip, you are very likely to get stuck on the lip. And maybe it's not like stuck, right, that you can't get yourself free. But if it's costing you time because you have to maneuver around it or you have to go at it at a particular angle, etc., that's something that could easily be prevented by just doing a little bit more ground clearance.
Right. There are also, to interject here, there are also some venues that that first holds events at where they the floor is not flat, where they run warped plywood in the venue, where you'll get variances across the field that are over 1/2 inch just from the corners of those plywood boards that protect whatever surface they're putting the field on. You will see some rises in the carpet there too that your robot could get stuck up on.
Yeah, certainly the carpet isn't nailed down to the floor. The floor may not always be the flat that's underneath it, and you end up with some ripples in the carpet. Or just over the course of the event, robots pushing and reacting against pieces, you tend to get the carpet bunching up in places. And you may think, well, the carpet's flexible, it's not going to matter that much, my driver will just compensate for it, which may be true, right? But if you've got a good driver that's got muscle memory, that might mess things up. Or in autonomous mode, if it happens to be in the wrong spot, all of a sudden the autonomous mode that you've worked really hard on doesn't work because the robot spins a little bit when it hits a particular patch and you didn't account for that. So really there's no excuse to have less than that ground clearance in almost all cases. The other side of things is when we have obstacles, right? So the example pictures I show below are for the bump in 2010. showing a mock-up 8-wheel drive in CAD and showing the clearance that's required in the chassis for that to be able to successfully navigate its way over the bump without interfering. Absolutely, if there's some kind of obstacle, I certainly recommend, if you have CAD capability, doing some simple geometry there. Also, 3D geometry can be important because not everything actually is 2D in the real world. And so if you come at things at an angle, all of your math changes. Scale sketches can work in lieu of that, or just mocking it up.
Yeah. We've
Slapping some
actually,
wheels on plywood. Yeah, Clint, go
yeah,
ahead.
I was about to say exactly what you said. We've actually taken 2 pieces of plywood, put pivot points for our axles to simulate it going over. This year it was the rock wall. Even in 2015, we even simulated it out of wood, going over that small transition to see if it bottomed out or hit anywhere. So whether you have CAD skills or even just kind of a little more grassroots approach to it, where you just mock it up and test it, is extremely valuable, because the last thing you want to do is go to your first event and you run into that, being high centered on a bump or something like that and prevent you from moving.
Yeah, it's really important to find these things out early, right? If you take the time and do a quick 2x4 and bolt some wheels on it, they don't have to be exact, but if you can get some idea of, yes, this drivetrain is going to have clearance for this, and I'm going to give myself some wiggle room, it's a lot easier to change things in wood on week 1 than it is to change things in metal at your first competition. Next slide. So then the next part of it is, how fast do you want to go? The general side of things is you want to be fast enough to do the tasks that you want to do over the course of the match. But you also want to be controllable. You don't want to eat too much battery or brown out the Robo Rio. Right? The higher you gear your robot, the more power it's going to draw as you accelerate. And that's going to reduce the available power to the rest of your systems, to the point where you may not be able to actually run your robot consistently through to the end of the match. I think it's really important to understand that your drivetrain is part of a robot, right? It's not its own thing. There are other systems that are going to take power, and you can't just assume that it's operating in a vacuum. The other side of things is that your battery voltage will drop over the course of the match. So if you do all your testing with fresh batteries and you don't run your robot for a full 2 minutes and 15 seconds, and you might not uncover some of the problems that when you're trying to go get your scale at the end of the match, and you've used up so much battery that your robot doesn't turn particularly well at that point, or it can't turn and lift the arm at the same time to get the hookup. That's something that is important to understand and to give yourself headroom for. If you're not sure, 9 to 11 feet per second tends to be a pretty good speed for FRC games with the motors that we have, and that's assuming that you're using 4Sim motors, the big black ones, on your drivetrain. And we'll talk a little bit more about motor selection later. There's also a lot of commercial off-the-shelf gearboxes that offer multiple ratios to use. You're going to hear us talk about the commercial off-the-shelf options a lot tonight. They're really, really good. You have to have a really, really good reason to not be using them. We're talking that some of the top teams in the world, Citrus Circuits 1678, 118 Robonauts, right, recent world champions, both of them are using commercial off-the-shelf gearboxes or commercial off-the-shelf wheels in many of their highly, highly competitive robots, just because there's no reason to be spending the resources and the time and the effort on things that you can buy. So it's really amazing. This is not stuff that we had even 3 years ago. And so a lot of drivetrain advancement was being done in the past that just doesn't need to happen today. And there's also a lot of really great resources. Bringing it back to talking about picking speeds, JVN's calculator is a spreadsheet that you can download that will help you figure out the real speed of your drivetrain and just how much load, and do pretty plots. And many of the gearboxes that you can buy actually have data sheets that talk about approximate speeds when hooked up to different diameter wheels.
And the thing to note on the kit apart chassis, a lot of times that's where most of the teams start at. You're given the kit apart chassis, it has a transmission, and a certain speed with certain size wheels. The thing to note is if you ever change those wheels, you really need to look at whether or not you need to change the ratio of that transmission. Like we talked about having a 6-inch wheel, that's going to affect how fast you drive. It'll probably make it actually where you go faster, meaning that you're going to have those brownout in situations that we talked about earlier. So if you change the wheel, evaluate and use JVN's calculator to determine if you need to also change the ratio at the same time.
Exactly. I can talk a little bit about Apex this past season. We used the kit apart chassis last year. It worked great for us. We ended up putting the 8-inch pneumatic tires on that many teams did. And if we had used the stock 6-inch wheels, it would have been a little bit too slow for my liking. Obviously, we have some mentors on the team with some experience. We knew that we would like to go a little bit faster, but when we switched to the 8-inch wheels, we did the math out and realized that was actually perfect speed with the original gear ratio. So rather than trying to change the gearing on it and make it go faster and then switching to the 8-inch wheels, we just put bigger wheels on and it solved all of the problems. So very important point, Clint, thanks.
Yep.
We've got a quick example calculation to show you just how easy it is if you want to do back of the napkin to figure out what your gear ratio should be. We're going to assume that we're trying to do a quick dash across the field, maybe going about 10 feet per second. This is good if you're going probably about 10 to 15 feet and you want to get there in an optimal amount of time. So we're going to be using 4-inch wheels, which makes the math easy because it's about 1 linear foot per revolution, 4-inch diameter times pi. And then 10 revolutions will get my robot 10 feet. So if I'm using sims in the drivetrain, the sim free speed, which you can look up on the various websites. Vex has a great motors page that's got all kinds of data, but the free speed of the sim is 5,000 revolutions per minute. And then we assume that once the sim has some load of the drivetrain, that it's going to be going about 80% of the free speed. So 4,000 RPM, which is about 67 revolutions per second. So if I need to spin the wheel 10 revolutions per second to go 10 feet per second, and my motor starts going 67 revolutions per second, I just divide the two, and the result is a 6.7 to 1 reduction. So that's, again, pretty easy math, all back of the napkin. If you want pretty plots, if you want to do different size wheels, if you want to look at acceleration pages, etc., again, the JVN calculator is a great place to start. Next slide, please. So the last thing, right, and one of the most important things is doing what you're going to do consistently. And that means maintainability and simplicity are paramount. The KitBot, as we've mentioned before, traditionally has been a very good option. Obviously, we don't know what the 2017 KitBot is yet, so we can't advocate for or against it. But historically, especially in the past few years, it's been an extremely solid drivetrain, and it's been hard-pressed for teams to find options that are that good out of the box. There are some others. Clint, yeah, go ahead.
The other thing is to remember that if you have the kit apart chassis, you're done with chassis. You don't have to design it. You don't have to do calculations. You don't have to do all these things. And you can spend more time and more effort on the things that do matter. Intakes, shooters, manipulators, elevators, arms, that kind of stuff. It's better to spend your time on those problems than trying to worry about creating this revolutionary, creative idea when there's already a good option, a really good option already available to you on day one.
Exactly. We're recommending that you run with 4 sims in the drivetrain. We'll talk a little bit about why later. But 2 sims typically ends up being too few. You're going to overwork the motors, and you're going to have electrical problems because of it. And more than that, you can put some real strain on your batteries and other things as well. So
yeah, and I think
yeah.
it's also important to point out that 4 sims is good because sims are heavy and you want your robot to have a low center of gravity. So put your heaviest motors in the bottom, and they're also up until 2 years ago. Yeah, up until 2 years ago, they were the most powerful motors. So they're the perfect drivetrain motor and you're able to use 6, so put 4 in your
Right.
drivetrain.
And I would
And-
say be very careful about using the 775 Pro real quick because we're on this topic. Using it on your drivetrain because those motors like to run at 100%, and where there's going to be times like with Sims, you're running at a lower speed, and it can handle those lower speeds more consistent, and they can take the damage and the wear and the tear. Whereas 775, if that's all you put on it, just because you see high power, high speeds with a 775. I would say be very cautious. The Sims are almost bulletproof when it comes to
Exactly.
drivetrains.
It's also important to note that historically, over the
Yes.
past couple seasons, there have now been 4 Sims in the kit of parts, where teams on day 1 they have all 4. You've got them. You might as well put them together when you're putting that chassis together.
Exactly. No, I mean the Sims are a proven commodity since 2004, when they first entered the FRC world. They are the gold standard of drivetrains. And the other gold standard of drivetrain is configuration: 6 to 8 wheel drive, drop center skid steer. In FRC, it's been proven time and time again. And we talk about drop center, we mean that the center wheel or wheels are a little bit lower than the outer ones. It helps with turning. You still get the stability of having your wheels spaced far out. The Kitbot, Vex Pro Drive in a Day chassis, the Versa chassis, the 220-1 Simple Tube chassis, these are all commercial off-the-shelf options, which are a variation on the 6 to 8 wheel drop center. Most top teams in FRC are using some version of it for all the reasons that we've listed. So before you do anything else, before you choose any other drivetrain style, ask yourself the question: does adding or changing the functionality of your drivetrain make your robot more competitive than adding functionality elsewhere? Because that's your choice, right? It's really easy to get into the game analysis and say, aha, the best drivetrain for this game is a swerve, so we should build a swerve, right? And the answer may be yes. If you're looking at just the drivetrain in a vacuum, it is the best drivetrain. But by putting your resources in there, you may gain some marginal improvement where you could have gained a big edge in your manipulator or a big edge in your end game by putting resources and weight, etc. there. It doesn't have to be the best drivetrain to be good enough to compete at high levels.
And this harkens back to that quote that we mentioned, that a drivetrain won't win you a competition, but it'll lose you one, in that it definitely does. Like, the best drivetrain isn't going to win you the competition, but a drivetrain that doesn't work is definitely not going to win you one. It's going to lose you one. We'll harken back to the quote, right?
Exactly. I will
Right.
keep coming back to it because it's so important. So that basically wraps up the fundamentals. Next, we're going to move into some more of the advanced topics, and Clinton's going to talk a little bit about picking your speeds, dash distances, and some other fun stuff like that.
Okay. So advanced section is optimization. We're going to remember our basics that we just talked about, doing things very consistently, and remember that our first rule that usually for most teams, priority number 1 is to move. Now you're going to want to take it to the next step. But one of the things I want to say about this is the hardest thing for any team to do is to evaluate one's resources and capabilities, right? You have to understand whether or not you have the funding, the mentors, the student base, the experience to be able to go to these advanced options for your drivetrain. Talking about getting better gear ratios, 2-speed transmissions, more traction. But remember, do not sacrifice the fundamentals that we learned about earlier.
Yeah, would you say it's safe to say that more than 50% of the teams can stand to spend a couple of years in the fundamentals to get it right before they even really consider moving on to advanced?
I think there's a lot of veteran teams that should go back to the fundamentals.
I agree.
There's a lot of teams. I mean, our team, we've made mistakes. I mean, we've decided to go certain directions with our drivetrains. Hey, I'll throw us out there. In 2015, we decided to do some Mecanim wheels because we thought, hey, we'd be able to squeeze between the glass and the totes and give us strafing ability, and we're not going to touch our opponents. We fought that drivetrain all season long, where there were so many teams that just did a basic tank drive, and they slapped the cans out of their way and performed much better than our team. Like so even veteran teams that have been doing this a while, they still sometimes go too far to the dark side and make a more complicated system than what they really need. So I think a lot of people should go back to just the basics. So next slide. I don't know if we're on then. Thank you. So the first thing that I think a lot of people try to look at is the ability to have a shifting option. The shifting option is great because you can get that higher end of speed to be able to go long distance quickly in your high gear. But when you get in situations where you have defense on you, or you have a situation where you have a bad battery or a bad connection or something, you can shift to that lower gear to ensure that your robot's not going to keep browning out and actually die on the field. 2012, there's an example of pushing robots up the bridge for balancing. A lot of times in that match, you would stay in your high gear while you're zipping around on the field trying to pick up balls. But towards the end of the game, you had to shift to low gear to push, maybe one, maybe even two robots up that bridge to get it to balance. In 2014, there was a lot of times where you had to bully your way through defense to move around and kind of make sure you could get close enough to take that shot. So a lot of times with the shifting, one of the things that we try to look at on our team is we talked about what the kit apart chassis has for a drivetrain. We talked about it being between 9 and 11. Our team, when we use shifting transmissions, we try to make sure that our low end is less than the kit apart's chassis, and our high end is faster than the kit apart's chassis. And that's to try to give us that competitive edge, maybe to allow for us to be stronger than the kit apart chassis, but also faster. But once again, you got to make sure that you understand how to build these, to put them on your robot. There's a lot of off-the-shelf options. The Sonic shifter, the ball shifter, West Coast products make some dog gear shifters and stuff like that. So there's a lot of off-the-shelf that you can buy and strap onto not only your kit apart's chassis that you get or any of those other off-the-shelf items. The next thing would be looking at adding motors, and some of the reasons why you might want to wonder why you might want to add motors. And most of the reasoning behind it is actually to get better acceleration. That better acceleration will allow for you to put your low speed at a higher, your low gear at a little bit higher of a speed if you have three, say, mini sims versus two large sims. The same thing goes when you're on the top end. You could set your robot to go 18 feet per second, but if you can never accelerate to that speed, it doesn't matter that you've calculated it to go to that speed. So you got to be careful. With the other thing with adding motors to be careful about is, putting, let's say, 3 sims on each side, and then you actually have the ability to trip your main breaker if all of those were to pull 40 amps at the same time. I think the main breaker is 120, and you can pull 160 amps. Main breaker goes, you're dead in the water, and we forgot about our fundamentals of always making sure we move. So the next thing is, talking about defining your sprint distance that you're going to have. So this is going to come into play depending on the size of the field. Is it a flat field that have really long distance to allow for you to accelerate all the way up to speed? Or is it a more condensed field where you got to do these short little 5 to 8 foot sprints? So next slide, I think we got the 2 slides that kind of show 2 examples of this. The first one that we see here is the 2011 logo motion. So if you look at it, we're kind of showing some arrows on here is the distance to those locations. So you have some fairly large ones, 54 feet, 36 feet to get back to the towers that you had to launch your mini-bots up. And then I think probably the most common one on this one was actually 27 feet. A lot of people would just go to the center of the field. So these are fairly large distance. So you might want to be able to have a higher top end speed, but ensuring that you could accelerate up to that. Like I said before, if you calculate to go 18, but you can never accelerate to that, there's no point in having that super fast speed, even though you get to tell the judges and maybe win an award off of it, right? Just kidding on that. So that's an example of long distance flat fields. Next slide, we'll go over. The next one shows optimization for stronghold. So in Stronghold, it was a lot smaller distance that you had to move. We had a lot of 10-foot or less movements to obtain a ball, to get to the outer works, then go over the outer works. So it's a very condensed, very tight field. So at that point, you don't really, I mean, we kind of said maybe 13 to 14 feet per second would be the fastest you would ever really want to go in Stronghold. I don't know what everyone else's teams kind of calculated. I don't know if we have any agreement on that, or
Sounds about right.
We went with a 2-speed transmission that was high gear of 14 and a low gear of 6, and we spent maybe 80% of our time at 6 feet per second.
Yep.
Yep.
Absolutely.
We were around 12.5 feet per second, and I think the best example that I have for Stronghold, 118, right? Robonauts, a really amazing team. They won 3 regionals last year. They won 3 regionals the year before. They won 3 regionals the year before that. They went like 10 feet per second last year, single speed transmission, right? Because you didn't need anything else with what they were trying to do. The longest distance that they were going most of the time was 10 feet. So why optimize for anything faster than that if you really don't need it?
I think the longest distance that you actually went in this year's game would probably be if you were a low bar cycler, where you had to go all the way down to the other end of the secret passageway and get all the way back. I think that might have been the only robot design, if you will, that would maybe have wanted a little bit faster of a drivetrain. But I would say for 90% of the teams or more, you could actually have had your top end speed a lot less than normal years.
Right, but even that low bar robot that's playing that is still probably not going to have that much larger of an average sprint distance because A, of how much stuff is on the field, B, how much stuff plus robots is on the field, and C, generally there are boulders that were a little bit closer than the very end of the secret passage for most scoring runs. So that average of 10 to 12 feet, it still holds true for a lot of your sprints.
Yeah, you're definitely not going to be going 14 feet per second over the outer works, that's for sure.
You could try.
I know a few robots that have, and they have 2 less wheels than they used to.
And I think there's a lot of teams out there that forget this step. They forget about actually saying, how far would we travel on this field? What are our distances? What is a reasonable distance for us to travel at any given point in the game? A lot of people skip that, and they just start talking, oh, we're going to make our robot go 22 feet per second, man. It's going to be the fastest robot out there. And it never achieves that speed. So, Nick, I think you're going to cover the next stuff.
So we've talked a lot about optimizing speed. Well, there's a couple ways you can do that. I'm going to go out of order here, but number one is traditionally in previous kit of parts chassis, the chassis have included a Tough Box Mini, which has the ability to, you can swap out that final gear ratio with different gear sets that are available from AndyMark. But in addition, other ways you can get that little edge in speed or lower speed is also sonic shifters. Those drop right into the kit of parts chassis, as well as other shifters like the Vexpro ball shifters and the West Coast Products shifters. They can be adapted to the kit of parts chassis, and Vexpro has published some really great instructions on how to kind of make the hole patterns line up and where you have to drill some holes to make it fit. But it's a pretty simple process to do that, and if you're using the kit of parts chassis, those shifters are also a great option too. You can also drop in some other gearboxes like the 3-sim for you, which is basically a 3-sim version of the Tough Box Mini. If you're willing to go to that edge and have 3 sims in your drivetrain but still want a simple single speed, there's also comparable gearboxes available from Vex and West Coast Products as well for that. But in addition to the kit of parts chassis that the majority of teams receive in their kits, there's also really other great chassis available too from Vexpro. They have the Drive-In-A-Day. They also have a Versa chassis. The Drive-In-A-Day being a sheet metal chassis that's also highly configurable in many different 6-wheel drive, 8-wheel drive configurations. They also have the Versa chassis system, which is super configurable. It's a West Coast drive style with cantilevered wheels and some infinitely adjustable bearing blocks. That chassis is great, as well as 221 Systems sells a drive chassis kit that's similar to the Versa chassis with movable bearing blocks and cantilevered wheels. As well, we talk a lot about chassis here, but even if you choose to go down the path of building a custom frame, it's pretty hard to shy away from all the COTS gearboxes that are available. You really need a darn good reason to reinvent the gearbox as a team when you're probably going to find something that is just perfect for what your application is from lots of the companies who sell parts to teams. Um, even buying a COTS gearbox to repackage in your own plates, that's still totally acceptable. Again, you'd need a really serious packaging concern to do that. But again, the internals of those gearboxes, it's pretty hard to shy away from them as well. So all that rundown list of ways you can increase, decrease, optimize speed. When you get into the higher speeds, though, one of the concerns is controllability, especially if you don't have a lot of space in your workshop or time in the build season to get driver practice in. Building a super fast robot may lead to some very funny surprises when you take the playing field, where your drivers may not realize that your robot's geared for 22 feet per second, and you end up slamming the opposite driver wall and possibly knocking somebody's controls off. So if you're going to choose to go above a normal 14 to 15 or even 11 feet per second, dedicating time to give your drivers lots and lots of practice to learn how such a fast robot drives is super important. So next slide, moving on from speed, is a little bit more about...
Sure, real quick, I want to say about the controllability. One thing that a lot of teams do to help that with their controls is actually squaring your inputs. This allows for your joysticks at the low, kind of near zero, have kind of slow movement, but as you accelerate and get closer to fully extended, it goes to that top end. It's not always the best, but it is kind of a nice way to get your drivers to have kind of that easier control of a higher speed drivetrain. There are a lot more advanced ways to do this, but squaring the inputs, it can work at times depending on what setup you have.
Right, absolutely. That's something that teams I've been on have done in the past, and it's made a huge impact in the controllability of those robots. Moving on a bit to traction and wheels, there's, again, lots of COTS options here of many different wheels that you can buy for your robots. There's two main types. There's replaceable tread wheels, where it's usually either an aluminum or a plastic body of the wheel where you can wrap a replaceable conveyor belt tread around, such as a wedge top tread that most companies sell, a rough top tread that it wear down a little bit faster, but they get you a little bit more grip. And you can get either Plaction wheels for AndyMark, or Vexpro sells traction wheels as well that you can replace either with those wrapped treads, or they also have replaceable rubber rings that you can replace throughout the season as they wear down. There's also permanently treaded wheels. There's everybody talks about Coulson's a lot. You'll hear that a lot. Those are great because they have super consistent performance. Even though they do wear down over a season, their performance as they wear is the same. So it's kind of while you do take a little bit of a hit in traction, the consistent performance, going back to one of your fundamentals of consistency, is an important thing to consider. Other options for increasing your traction with permanent treaded wheels also include softer high grip wheels. Now, this comes with a bit of an asterisk because the softer tread, as I spoke about earlier with the wedge top and rough top tread, the softer the tread, the more often you're going to have to replace them. So you have to make that choice of, I want this performance gain versus maintainability. So, okay, I might have to replace wheels at one point during the season. And that's kind of an asterisk with those softer high grip wheels. So the reason why you would add higher traction wheels is really to get you that competitive edge, primarily with pushing matches when you're being defended and need to get yourself out of a situation versus a standard kit of parts chassis having that traction edge will help you get out of those defensive battles. That being said, there is such a thing as too much traction. Having too much traction, definitely number one, can increase turning scrub, which will reduce your turn speed, and you'll take a hit on battery life as well. When you're trying to play a maneuverable game and you struggle to turn, well, okay, you kill that battery. Again, losing one of your fundamentals, you're not moving through the whole match. As well, too much traction can also make getting out of a T-bone situation. Now, a T-bone situation is where two robots are locked together with their bumpers and usually an open field where one robot is perpendicular to the other, and the defending robot is pushing a robot across the field. And when you get those bumpers locked together, having too much traction where the defending robot can sink further into your bumpers makes it hard for you to turn out of that defense situation. So there is such a thing as too much traction, and it's important to consider these things when selecting wheels for your robot.
And a lot of times, one thing that you can do, a lot of people always think about pushing and shoving and, thinking, no one, a lot of people joke, you don't push truck, right? They push you. So
nobody pushes truck down.
So the idea is, that they have to go through. Now, the other approach to that is there's nothing saying you can't go around. So sometimes being more agile, and not try to go through people and zip around them and find the opening can sometimes actually be more beneficial than just trying to go straight through. Once again, this all depends on game analysis, what you determine is going to be popular in the game. 2014, there was a lot of open space for you to drive around, and having a partner give you kind of a pick to go around them, find that opening was much easier than trying to just shove your way through one of your opponents.
Yeah, and mentioning 2014, there's the other side of it, which is, you can put Omni wheels on your drivetrain, as a lot of teams did, and just say, you know what, we're not going to have any traction laterally. And it takes, obviously, they had to commit to that early and make sure they practiced it so their drivers were used to sliding all over the field and still being able to
Killer
take
beast,
a shot.
prime example.
But, I mean, you look at how effective that can be, so that's kind of going the opposite direction.
They thought they were nuts going with that design at first, and then it paid off for them so much. The other thing that was great about that design, I don't know if many people know about it, it was a single reduction. I forget what the reduction was, but it went from the sim motor to the one gear to a 4-inch Omni wheel, and that's it. The efficiency on that thing was awesome compared to most drivetrains, and the goals were so large, they didn't have to hit, a small window in the top of a tower. They had to basically hit half of the field, which is 15 feet wide of a goal.
Yeah. One of the other things to consider when you're looking at traction is as Nick mentioned, having to replace wheels over the season. Depending on what your chassis configuration is, that may be difficult or that may be easy. For example, if you are using the kit of part chassis, you have to take the side plate off if you want to replace the wheel in the middle, because the gearbox is, in previous kit apart chassis, the gearbox is built into that side rail. So think about that of like, well, maybe I don't want to run really soft wheels in the middle, because then you're going to be in the middle of the competition, your tread's all worn down, and you're trying to take the side of your drivetrain off in order to replace this thing. So, definitely some considerations there.
Yeah. So chugging along a little bit to sensor integration. This is a lot. Sensors are a bolt-on thing that you can work with specifically in your drivetrain to, number one, is to have repeatable autonomous routines. You can add encoders to your drive gearboxes, which many of those commercial off-the-shelf gearboxes, they support. Optical encoders such as the US Digital E14 encoder. There's some Greyhill encoders that are supported. You can also add an IMU, which is an inertial measurement unit, which is a fancy device that measures things like angular rate, acceleration, etc., that you can plug right into the Robo Rio. As well, you can also put basic gyros on, which tell you angle of where you've been from a relative point. You can plug those right into your robot. And providing this feedback to the RoboRio of where the robot actually is versus where you think it is will give you more repeatable autonomous routines and drive commands in general. For example, you'll get a lot more robust or repeatable drive commands, such as asking the robot to drive forward for 100 ticks of an encoder versus 3 seconds, because different periods of a match, that 3 seconds is going to be at X battery voltage versus later in a match it will be at a much lower battery voltage. Using actual sensor feedback to get feedback of where you are versus where you think you're going to be, to allow the robot to compensate and calculate, will be a much better or more consistent way to move your robot, so to speak.
Yeah. And with encoders, you don't always have to put an encoder on each side of your drivetrain. A lot of times, just adding that one encoder to one of the sides, you don't have to invest in the cost of both, and that'll give you a lot of information to improve and increase your repeatability of your autonomous.
Right, absolutely. There's also other sensors as well. There's like ultrasonic sensors that some people use, which are great for really close-up adjustments. But that's kind of more overall robot picture for those. But you can still use those to provide feedback to your drivetrain. That's actually all I have on sensors. And as well as some of the specific parts you can use to get these advanced value adds, so to speak. So there's that one little extra bar where going full custom or some of the off the wall designs, or that little extra edge, that's what we call expert.
So
and I think go ahead.
So you've now spent, I'd say, at least 3 or 4 years working on the fundamentals and the advanced topics that we've covered so far, and you now feel as though that you're an expert and the only thing holding you back is your drivetrain. And this is the type of tier that we're talking about here when we talk about expert drivetrains. And the one thing that expert drivetrains, or that you can do it when you're an expert, is try to use your drivetrain to actually get an advantage on your opponents. Beforehand, your drivetrain allows you to use your scoring mechanisms to get your advantage, where this is actually trying to get a strategic or a maneuverability or a power advantage over your opponents. So the way you do that mostly is through different types of drivetrains, space or weight savings, motor selection, and all of this, of course, is without sacrificing the fundamentals. One thing I want to point out here is, notice that we've been talking only tank drive for all of the going on 40-45 minutes that we've been talking this entire time. And that's important because a tank drive is, in my opinion, and probably the other three's opinions, the best, hands down, the best drivetrain that you can make in first. That,
Agreed.
Across the whole spectrum of things.
From an overall standpoint, absolutely.
If
Go ahead.
I was going to say, if every team in first had if first had to dictate that teams could only use one type of drivetrain across all of first, hands down, they should give them a tank drive.
Yep. I think one thing that's important to mention as we delve into this sort of expert topic is that the highly customized drivetrains that are trying to get this advantage, a lot of it is highly dependent on the specific resources that each team has available to them. And we're talking time, we're talking students, we're talking machining capability, etc. Problems, money, right? Various particular problems that they are trying to solve. We're talking about a problem-solving approach here. So I think that's really important to keep in mind as we go through this last expert topic, is that just doing a mechanism because a mechanism seems cool is not the same as, deciding to do a particular swerve drive because you absolutely have the capability of doing that swerve drive and you're committing to that for multiple seasons.
Right. So the first big thing that you can do to get another advantage in your drivetrain is to change up your motors. And we touched on this a little bit in the intermediate area, or sorry, in the advanced area. And I think we see a transition eventually coming. We touched a little bit on this in the advanced area, but we want to get into the only three motor options that I would support putting in a drivetrain that are spinning the wheels. Turning the wheels is a whole different story, but you shouldn't be turning your wheels anyway. So the first is the sim. We've talked about it. It's the gold standard. It's very robust. It is heavy and it's very powerful. Then just recently we had the mini sim come in, which is a lighter, less powerful, but it is just as robust. So, for example, we mentioned that having 6 sims can really tax your battery and can draw too much current. There are some teams that are putting 2 sims and a mini sim in to gain that extra with little risk. You still run the risk of browning out your robot, but it is less of a risk than 6 sims. And then finally, the 775 Pro drivetrain kind of made its debut last year in a few teams. A few teams let the smoke out. A few teams did really well, and they're playing with it this year mainly because there's some serious weight and space savings that you can do because it's such a small and light motor, as you can see here. But the problem is that it's air cooled, and an air cooled motor can burn up very fast if it doesn't have the fan that's built into the motor spinning to blow air along it. So in a drivetrain, if you're not geared such that that motor will never stall, and you stall that motor, it'll burn out very fast. And something that's also very important to note is motors can quote unquote burn out without releasing the smoke, and that they can become seriously degraded throughout if they get too hot for too long, too often. And you can find out that you just don't have the power to get where you want to come the finals.
Yeah, there were a few teams that were susceptible to that. This is a good example of there's a handful of teams that are looking at that tried it last year. There's a handful of teams that are looking at it. Anybody who's considering running a 775 Pro in their drivetrain, either as a mixture with sims or as its own, I would highly, highly recommend you do some actual testing with it. Design a test bed, push it to its limits, get some real data, because it doesn't exist yet. The motor was introduced last season, right? And traditionally, air-cooled motors do not perform well in drivetrains. So it's new ground.
A good example for us, we were very young. We were a sophomore team back in 2009. Everyone knows about 2009. You didn't need traction. You didn't need all this kind of stuff. And we had the crazy idea to use, I think it was Fisher Price motors.
Prices back in the day, yeah.
On our drivetrain, and they were air cooled. And after using them for so long, they weren't cooling enough. They shorted to the frame, and we were out. I think at Lansing, we were out of commission for like 3 hours because we couldn't figure the problem. And come to find out, is that the housing was shorting to the frame. So like ever since then, it's like never ever put just a single air cooled or only air cooled on the drivetrain. We would hesitate, but I don't consider us at the expert level of advancing our drivetrains at this time.
And the next important thing in expert levels is your space and weight savings. And this is really where you get away from the COTS frames. And this is really in my opinion, where you can really get stuck in the weeds here. It's a matter of, if all the others are a matter of choosing the right wheel, and unless you're making your own wheels, then you can't really get too lost there. You can burn a 775 Pro and get really burned there, but here you can lose time in the design phase. You can lose time in testing. You can really end up fighting this thing through the whole competition season. But there's some really cool things that you can do if you're an expert drivetrain team. One of those things is a sheet metal chassis. And you can see here, this is 971s. This is, in my opinion, the top 1% of the top 1% of expert level drivetrains, in that it's a sheet metal chassis that is stiff and riveted and incredibly light. They designed it in-house and had it made by their incredible sponsors. But like we said, they designed it in-house. So they took design time out of out of their mechanisms, or they used resources that they had to build this thing. And if you don't have that, then I don't think you should bother.
And for that robot, they actually spent time in the off season testing and working with that octagonal shape and seeing which design worked best. It wasn't just like, hey, they heard the game come out and threw it out on the field.
Yeah, I mean, I think it's worth mentioning here how much time went into this chassis. The basic design of the chassis is still the same basic design that they'd used for 2 previous seasons, 2012 and 2013. They modified it over the off season after experimenting with octagonal frames, like Clinton mentioned, to add the hexagon to it, but it was a modification on a proven design that they'd already been running in competition for 2 seasons. This wasn't a spur of the moment. I think that Hex would be good here, so let's try and build a Hex chassis.
And speaking of Hex chassis, there's some serious advantages here. In 2000, I'm not sure exactly when it happened because I'm old and things are falling out of my head.
2013 was the first year of perimeter-based.
Yeah. So frames are based, the size of your robot is based off the frame perimeter now. So as the shape of your frame becomes closer to a circle, you have a larger area of your robot to frame perimeter ratio, which means flat out you just have more space inside of an octagonal robot. And in 2013, you guys built an octagonal robot, right, Clint?
Yeah, we actually did. We read it in the rules, and we looked at it and said, wow, this gives us a lot of different options. It allowed for us to have a larger storage area for the Frisbees, but it came with other problems that we ran into. So the starting configuration was very difficult for us that season because of the octagonal shape that we had. But we also noticed some of the benefits of having that octagonal shape is that it allowed for us to get out of the quote-unquote T-bone situations that people would try to pull on us, where they would try to push us on our side. And because we had these smaller areas to kind of pivot off of, it allowed for us to be a lot more maneuverable on the field. So, like I said, they have their benefits. I like the fact that First has switched this to the perimeter. It allows teams to be a little bit more creative in their design instead of always being, sorry to say, a box.
Yeah.
And then finally, the kind of a niche thing that kind of popped up in the past year or two is this blank in tube idea, in that there's a lot of teams that make their chassis out of tube stock, and those tubes are just taking up space and they're hollow. So they have the idea of stuffing things inside, and it saves you some cool things inside the frame perimeter, but it makes maintenance difficult. And as pointed out here very deftly at the bottom, is you can't just rivet things to your robot anymore, because now you've got hidden things inside your tube. But if you pull it off, it does look awesome.
The big thing on this is make sure that you have a game plan for how you're going to maintenance, because guess what? That chain's going to break, timing belt's going to break, something's going to catastrophically happen inside of that tube, and you're going to have to get to it, and you don't want it to be the finals of Einstein.
Right. There are ways around it by building extra drive modules and having them in your pit. The problem with that is that it takes away from your withholding allowance for parts that you could be using to upgrade other mechanisms on your robot.
And finally, we finally get into the non-tank drivetrains. I know a lot of you came here to watch Behind the Lines to hear about how do I swerve. And basically what our answer is, just don't do it. If you do it in a methodical, well thought out, well practiced, scientific and engineering style. And there's a lot of resources that can help you out here. 1114 for years has had one of the pinnacle presentations on how to choose the drivetrain, and they pretty much say things along the same as us. If you want to go ahead and do a non-tank, then sure, but tank's going to be 99% of what you want anyway. And finally is this weighted design table, which could basically be given an entire presentation on itself. But there's a link in the document that we're going to be sharing after this episode that allows you to give weights to what you think is important and then rank all your different designs based on, or score all your designs based off of what all those things that are important. And it kind of gives you this objective way to just say, look, Tank gives a score of 111 as shown here, whereas Butterfly gets a score of 74. So objectively, Tank is better or something like that.
And that's going to be extremely game specific. I mean, that's
Mhm.
going to be game specific. I mean, you look at a team like 1114. I think since 2008, they have had a tank drivetrain, except for 1 year. And the only year that they didn't was 2015, where you weren't interacting with your opponents. And you know what? They actually went through this weighted tables. And honestly, my personal opinion for 2015, the Kiwi Drive, honestly, was probably the best drivetrain for that if you noticed it at the beginning of the year. And they did that because they evaluated their drivetrain for that season's game.
Yeah, and the key to that drivetrain as well is choosing the Kiwi Drive allowed them to build a robot that actually fit in the landfill. A traditional Mecanum Drive or Swerve Drive, you have to deal with that odd corner that hangs on the scoring platform as you're trying to strafe your way through the landfill to pick up totes. And the root point of that is they identified that a specific important game task could be made much easier for them without actually sacrificing the rest of their gameplay, because they had it, because the field was divided that year. They didn't care about being pushed around, so that specific drivetrain for 1114 proved to be a significant value add without really hampering the rest of things.
I mean, it's only 3 points to make a plane, and they always had 3 wheels touching the ground. Where our team, we used Mecanum that year, and we struggled with having times where one of our Mecanum wheels were not touching the ground, and it really affected how we moved down the field. And once we saw them, it was like, wow, we didn't do our homework to evaluate Kiwi, because most people every year ignore it and throw it off.
Right.
Yeah, I think it's really important if you're going to use this weighted design table again to think back to what we said at the beginning of the presentation about not designing in a vacuum, right? And it's easy to fill out this table and not give enough weight to things like difficulty to build or maintain, or the amount of resources that it takes, because you're thinking about it from a drivetrain standpoint and not from a robot standpoint. But the last point I think to mention here, and we're going to go into questions right now. I realize that we're sort of at the hour limit. I think this is a really important presentation, so we're going to stay on and answer some of the questions. And the VOD of this will be up on YouTube shortly, as well as this presentation that we have will be posted online. But I think the last thing to mention that's really super important is that 1114, we talk about this 2015 sort of seminal year for them. They have had so many years of success with drivetrains, and they chose to do it because they had confidence that the rest of the robot could be built well, and that drivetrain could be built well, because they have a keen understanding of how it works. It was, again, not a snap decision. And it's I had one other point to make, but I forget. So we're gonna, I think, move on to questions, unless we have any last points from our guest here. No, all right. So our first question is, what about drivetrain construction? Is it better for sheet metal frames, VersaFrame, C-channel, etc.? And as we go into this, we should mention once again, if you have a question, go ahead and submit it on Twitch chat, !Q, followed by the exclamation by your question, on Twitter with the hashtag FRCBTL, or email btl@frcgamesense.com.
So I think something that that'll be part of every answer we give out is going to be the answer to this one. And that was hard to say for some reason, but the best drivetrain for your team is the drivetrain that works for your team. If you have a sheet metal sponsor that is begging you to give you sheet metal work, then build a sheet metal drivetrain and have them help you design it. If you don't have any machining capabilities whatsoever, use the kit apart chassis or buy VersaFrame and the VexPro stuff. The best drivetrain construction is the one that your team can make the best.
Absolutely. And every um, versions of this are available from top teams for sheet metal drivetrains, for West Coast drives. A bunch of teams have made their CAD models available. You can go look at what other teams have done successfully. I would highly, highly recommend it. I know 1114 has previous CAD available.
Best sheet metal team in the business have theirs up online. 148.
Yep. 148 has it. 971 has it. I think Citrus Circuits just posted last year's. That's a tube drive. Robonauts have everything back to 2011. So there's a lot of resources if you're looking at how to build a particular one because you have the resources for that.
Mm-hmm. All right, our next question is, when should I use an 8-wheel drive versus 6-wheel drive? I've seen teams use both on flat field games.
I'll take a
This
stab
is an
at it.
interesting one for sure. Clinton, you were going to say something?
I have my preference and reasons. So my personal preference on a flat field is an 8-wheel drive. A lot of that revolves around by having how do I explain this? By having 8 wheels, you have 3 different sections that the wheels are closer together. This allows for you to have better turning ability. So if you think about a wide robot, it can turn really agile because the wheels are really close to each other. When you have an 8-wheel drive, that allows for that to happen in 3 different locations. The other benefit is that you typically would drop the bottom 2 wheels down and have the outside ones up slightly. The great thing about this is this allows for you to have a very flat, consistent level robot at most times during the match. So if you think about this year's game, people that had a 6-wheel drive, you're going to either toggle forward or you're going to toggle backwards on your wheels. So this is going to affect your trajectory of your shooter going into the goal. So with an 8-wheel drive, it allows for you to kind of have that very flat foundation, always a place to go back to. So my personal preference is 8-wheel drive. I love like a smaller wheels if it's a flat field, 4-inch wheels, 8-wheel drive, very low center of gravity is what I would prefer.
Yeah, I feel a lot of the same way. That the advantages of a stable 8-wheel drive are pretty hard to shy away from. The only thing you have to consider when choosing an 8-wheel drive is the weight difference between an 8-wheel drive and a 6-wheel drive. There's a little bit more weight because you have 2 extra sets of wheels, axles, chain or belt run. You have to consider that. That being said, having that weight down low is never a bad thing in a drivetrain. Weight down low in an FRC robot, keeping your robot from tipping, is never, ever a bad thing.
Sorry. I definitely agree with what was said here. 6-wheel drive, you could get away with a little bit less weight. Some teams really prefer the 6-wheel drive. I know 971 prefers 6-wheel drive. It's worth keeping in mind that they're very good at getting their center of mass to a specific location on the robot, right over the middle wheels, and they use alternate advanced control schemes to make the robot more controllable. So the 6-wheel drive has a tendency to skid out when you go through turns because you'll have it rocked in one direction and it'll be turning, and then centrifugal force kind of rocks it in the middle, and all of a sudden it spins around on you. So I like 8-wheel drive because they tend to be a little bit more maneuverable. They let you get away with smaller wheels and still maintain good clearance over obstacles, but the flip side to that is it's more chain, it's more pulleys, it's more belts, it's more things to tension or make sure they're right. So the 6-wheel drive kind of is the simpler version of it. That's the answer.
Yeah.
That's my answer.
All right. Our next question is, how much driver practice is enough driver practice? if I know my team can't meet a lot after build season, does a more maneuverable drivetrain make more sense? And this is good. This is a good question because it shows a good big tripping point of teams in that first of all, there's no such thing as enough driver practice.
True.
You should just get as much as you possibly can all the time. Schedule what you can. If you can get an extra drivetrain, even if it's not like an identical practice robot, if you can get an extra drivetrain or an old drivetrain to drive around, then it's great. But what I think the most important thing to hit on here is if I know my team can't meet a lot after the build season, does a more maneuverable drivetrain make more sense? And the answer is just flat out no, because a drivetrain is only as good as the drivers that are running it, and the simpler of a drivetrain that you can go or that you can make, the sooner that you can start practicing with it.
And the
Right.
easier that they'll master it as well. I've seen so many teams build a swerve drive, and then their driver goes out there and drives it like it's a tank drive because they never got any practice, and that's what they're used to.
I've seen multiple people do that with Mecanum drives.
Mhm.
You know, they want the Mecanums. The design group wants Mecanums. They put Mecanums on the robot because of all the strafing. And what do they do the whole season? They drive it like a tank. They drive it like tank drive, having it turn, never strafing, hardly ever. The more maneuverable drivetrains are honestly actually probably harder to learn. So that means you're going to need even more practice with a maneuverable drivetrain versus a tank drive kind of a drivetrain. The other thing is, it sounds kind of crazy. Nothing ever said you can't have, get a little RC car or something like that and have your driver drive an RC car around if it has kind of a similar drive fashion, or if you have access to a Vex team or an FTC team or something like that that have a robot, you can build a small robot to simulate how it maneuvers and drives around a little bit more than just getting access to that robot.
I think that pretty much answers that one. Next question we have is, what are the pros and cons of West Coast Drive? This is a good one. There's actually a thread on Chief Delphi about this as well, which I think had some pretty good discussion on it. Nick, you wanna take this one?
So there's two really big pros with.
Actually, before we start, let's level set on what West Coast Drive is, because I think there's not everybody knows, and certainly everybody who thinks they know doesn't know.
So West Coast Drive is traditionally a tube-based drivetrain. Some people have made sheet metal variants of this, where the wheels are cantilevered, meaning that they're supported by one set of bearings on one side, and the wheels over here, imagine my fist is a tube or something. And the wheels are supported only on one side, and there's usually a bolt or something that just keeps them from coming out, and there's not a bearing on the other side. So there's no frame members on the outside of the wheels. And they're either driven by chain or belt inside the tube or beside the tube. And that is a true West Coast drive, and it gets its name out of California, primarily out of 254 and teams like that, who have built these 254 and 968, who built these drivetrains way early on in
2004, 2005, 2006 area.
Right.
I think 60 was doing a version of it back in 2002, but it's important to remember that these were also developed back when COTS wasn't really a thing, and when bumpers weren't a thing. And both of those are kind of important points. You keep going, Nick.
Right. So the number one advantage of West Coast Drive, if done correctly, is weight. You save a lot of weight because you don't have those extra frame members to hold all the bearings and hold the wheels in place. You do all the cantilevering and bearing support on one side of a drive module. There's less frame, less weight. So definitely number one is the weight savings of West Coast Drive. Number two is accessibility of the wheels. If you're running those softer treaded wheels where you need to change them, a lot of these designs, they have an axle, a live axle that the wheel sits on, and there's usually only a bolt or a retaining ring holding that wheel in place, and it's one screw for a lot of these designs, one screw per wheel, and that wheel's off, and you can change the tread on it or replace it with a new wheel way faster than you could with a traditional plate drivetrain. Those are the two big advantages of a West Coast Drive. The cons is it's somewhat difficult for teams without. It used to be somewhat difficult
Yeah.
for teams without machining resources to build one. Now with VersaFrame, it's a lot easier because they sell all the brackets, the tubes, the bearing blocks that you need to build a robust West Coast drive. You still have to consider things like a solid rigid belly pan will hold the thing together and putting cross members in. The biggest con of West Coast Drive that used to exist was how hard it was to build, but thankfully VexPro has brought West Coast drives up to teams who maybe don't have those high level machining resources.
They've brought them east. Yeah. No, I definitely agree with that. I think you know, build quality is a big part, as we mentioned, machining resources. But if you're going to use some of these COTS items to build it, be very, very vigilant about the quality of parts that you're making, because it will have a much, much bigger effect than on maybe a more traditional drivetrain where you can run it with a dead axle. That's where the wheel has the bearings in it as opposed to running on a shaft that's spinning. So structurally, it's a little bit different. And you can build a lot more tolerant designs without not doing West Coast Drive. West Coast Drive really requires you to, if you're not going to do it with precision machining resources, at least put a lot of care into it.
I think
Yeah.
the biggest thing that allowed West Coast Drive to become something that you can build from COTS is the COTS hex shaft.
Yeah.
I think that's the fact that you can just go to VexPro or AndyMark and just buy hex shaft and put it in a hex broached wheel that is also commercial off the shelf, and slap them on some rails and put some chains on it, and you've got West Coast Drive is just awesome.
And not have to mill all 6 sides down because the hex you bought is 505, 510 or something.
Oversized.
Mhm.
Yeah.
Yeah.
No, I think overall, from a competitive standpoint on the field, other than accessibility for replacing tread and things, there's not a whole lot of advantage or disadvantage over a equivalently built non West Coast Drive. Top teams with sheet metal typically don't do West Coast Drive because it's not suited for their machining resources. Top teams that have a lot of CNC mill tend to gravitate towards West Coast Drive because it's easier to build. That's kind of the end of it. I think it's just whatever is easier for your team to make is, like we said before, going to be the best one. There isn't so much of a competitive advantage these days that it's worth going out of your way to build a West Coast Drive, in my opinion.
Oh, you hurt me deep there, but I'm not going to get into an argument like almost an hour and a half into this. We'll take that offline.
All right, I think we got one last question. Ty, you want to take it?
Sure. The final question of the night is from BJ Simons or Simmons. Probably Simons because 1M. Any tips for designing for maintenance? Plans to access motors, for instance? Nick, you can go first.
So accessing motors, number one, is a thing you should do, and have
End of show.
End of show. Yes, we talk a lot about sim motors being the be-all, end-all motor for a drivetrain. They still break too. Especially if you're reusing sim motors from previous years, they do eventually wear out. The brushes can get so dirty that carbon builds up on them that they no longer spin. Sometimes you just get a motor that's dead out of the box, or the rarest of all is actually letting the magical smoke out of a sim motor. It can be done after, especially during autonomous, where you may get in a situation where you stall your wheels for 15 seconds. I've seen it done. Designing your chassis such that you can still access the motors, or using COTS gearboxes that have motor access, great things. That's probably one of the biggest things, but also if you're going to go down the route of designing custom chassis, being able to actually remove your drive gearboxes within a matter of a couple minutes during an event is super, super, super important, especially if throughout an event you run your robot really hard and you don't especially in a district, and you don't have time to tear that gearbox apart and re-grease your gears, debris gets in those gearboxes. You end up wearing those gear teeth down very fast. Being able to remove those drive gearboxes and replace them in a couple of minutes is super, super important. And there's a couple ways around that, but that's big thing, really.
I think another great thing to say about this is that one of the best things for maintenance is preventable maintenance. I don't think we talked about it at all this, but grease your transmissions. Ensure that you have grease on them. There are so many competitions I've went to where people have not greased their transmissions. They're dry. They turn into little, star-shaped gears instead of, being the proper shape that they should be. The other thing is, know that things are going to happen. If you use chain on your drive, that chain will probably pop off and break at some point. So what do you do in that situation? One of the bigger ones that I think are sometimes a little bit more harder to deal with is timing belts. If you're using timing belts, a lot of times as your design starts going further and further, you have standoffs or you have support structures that go through the center of that timing belt. If that timing belt breaks, how are you going to get that timing belt off and actually be put back on your drivetrain? The other thing to consider that I think a lot of people a lot of times is having access to the bolts of the motors. So that means your outside frame rail, you're going to have to put a hole in the same location that the motor is within internally inside of your robot, and honestly, drilling a hole inside in that gear so that the Allen wrench can fit through and actually get access to that. A lot of times people are like, oh, we'll just take the motor off. We got plenty of room on the backside to move it back and take it out. Yeah. But if you can't get to those bolts, you're never that motor that you have on that transmission. So kind of anticipate those things. And to reiterate on the thing Nick said, I think in 2014 for us, we actually set a goal was to be able to change out one of our wheels or one side of our wheels, or I think it was one side of our wheels within a minute. That was our goal. We ended up, and we had an 8-wheel drive that year. I think we ended up getting it to where it was about 15 to 20 seconds we could swap out a wheel.
Wow.
And a lot of that was we had a dead axle. You pull the axle out, the wheel dropped down, change it out with a new one. We use all off-the-shelf items. That way we didn't have any custom machining or custom attaching, and we had spares made, ready to go to get slapped back into the drivetrain to get us back out on the field.
Yeah, I think spares is a really important point. If you're going to buy a COTS gearbox, I would certainly recommend buying one spare to have ready. You just don't know what's going to happen. If you're building a custom one, have extra parts. I think usually you don't have to plan for dual failure. Usually just having one full set, but extra wheels, extra sprockets. I mean, we've seen sprockets just run down till the teeth all shear off sometimes. And just understanding that you can build the most bulletproof drivetrain ever, and stuff is still going to happen. I was with Skunkworks in 2014, and at championships we lost a qualification match because a 5/16 set screw managed to get itself kicked up from the field, not from our robot. We have no 5/16 on our robot. Somebody dropped a 5/16 set screw on the field, kicked up, managed to wedge itself in one of the teeth of the drive sprockets, and zipped the whole chain off. And that was it, right? We had one drive side for the rest of the match. So, stuff happens, and it may have nothing to do with the way that you built your drivetrain, but just planning out and at least thinking through what the steps are going to take once the robot's all together. I think Clint had a good, important point about access to bolts and things. Like, it's really easy to put your drivetrain together and be like, man, this is great. And then you don't think about it when you put your superstructure on top, and all of a sudden, like, somebody's got their head and an arm and an elbow around trying to get that Allen wrench, half turn at a time, because you can only fit the angle in there to undo a bolt. And that, 2-minute drivetrain swap is not 2 minutes anymore.
And the great thing about having COT items on your drivetrain is you can bring them in and they don't count against your withholding allowance.
Yeah.
One of the things we did in 2014 again was we made it where our replacement wheels that we did were 100% COTS items. So that way, when we got to the event, we could assemble them at the event. So they came into the event unassembled, put a couple bolts in to put the sprockets on and the bearings in, and we had spares ready to go, and it didn't count against our withholding allowance.
Right. And yeah, I will always try to use COTS components specifically so that I don't have to, or a team doesn't have to tap into that withholding. And that really goes for the whole robot, but specifically for drivetrains, having those wheels ready to go, having full COTS gearboxes ready to go, again, is super important.
No, I mean, I've been talking to a few people on some really, really top teams that have done custom wheels traditionally for almost a decade, right? And are talking about going to Coulson's or other COTS wheels because it's just not worth it. It's not worth the machining time. It's too hard for us to make these. It counts against the withholding allowance. Like, just I'm gonna go do some testing, figure out what's the best COTS wheel I can get, and roll with that.
Yep. Yeah, if you can use COTS materials or even a whole COTS drivetrain like the kit chassis, then do it. It's going to save you time. It's going to save you trouble. Other people have done the engineering. One of my favorite phrases is from 1678, and steal from the best and invent the rest. If you can steal a kit chassis when they're giving them to you, then do it. Well, that about wraps us up,
Don't
guys.
actually go steal a kit chassis. Figure of speech. Just important clarification.
Yeah, steal it from the kit chassis that you get given to you. That about wraps us up, guys. It was a long episode, but we feel as though we got through a lot of very important information. Just remember to stick to the fundamentals. Have a drivetrain that gets you where you want to go, when you want to get there, and consistently, and you should have a much happier season. All right, we'll see you guys next time. Have a good one.
Thanks, guys.